Hello, I'm Edward Dunne. I'm the executive editor of Mathematical Reviews. I'm happy to have this opportunity to introduce you to the new generation of MathSciNet. It's been a big project, many people involved. All of us are excited at the better and broader functionality that it provides. As many of you know, MathSciNet has been the web-based user interface to Mathematical Reviews since 1996. That interface gives you access to a database of over 4 million items created from the work of our 74 current staff members and the more than 25,000 reviewers. It's time now for a big change in MathSciNet. In particular, it's time for a new user interface. The biggest changes in this release are new, clean, modern look, improved functionality for tablets and phones, and increased accessibility for all users. Elements of the new interface have been introduced over the years. We added filters, also called facets, in late 2016. These are modeled on the filters that show up when you're searching a retail site or a library catalog. The filters show users how many items in the search results contain a particular element, such as an author's name or the title of a journal. You can then select that element to refine the search results. Filters are powerful because they use the richness of the database itself to point users to more productive searches. The profile pages for journals were expanded dramatically in June 2019. Indeed, the journal profile pages became a prototype for the look of the new interface. More significantly, the revised journal profiles advance the idea of giving users a detailed picture of any journal based on the data from its publication history. Few things that you're going to see as I go through this demonstration, this webinar, are that the primary interface is going to rely on a single box plus field codes. By forming the search this way, it's more familiar. A lot of people are used to the single box that you find in search engines and many other places. But it also means that you have access to about twice as many different fields from the database for any of your searches. If you prefer the classic interface, it remains available with the click of a button, as I'll show you later. We've also improved the filters by allowing more variability in them and more access to the data. We've also broadened the implementation of autocomplete. And best of all, it's still the amazing database behind it all. Before diving into the details, let me point out that there are 4 primary searches in new MathSciNet. These correspond to the major parts of the database. The most common search is the publication search. There you're looking for papers and books. There are author searches, journal searches, and series searches. You can see those here in the new interface that I've just brought up on screen. Publication search, author search, journals, series, and of course, because MSc is behind so much what we do, there's an MSc search. With a publication search, typically you're going to be looking for one or more publications, a list of articles, a list of books and articles. For an author search, you're actually looking for a person, the person who is writing these articles and books. And an author search will usually lead to an author profile page. Journal search looks for journals, usually leading to a journal profile page. And series search looks for book series, whether they're monographs or collections, such as proceedings volumes, and that will lead to a series profile page. The biggest change from MathSciNet is that the publication search is now through a single box, as you see here. You can enter some terms in the box, then either click the search button or hit return or enter on your keyboard. and the search will be executed. So let's show that off a little bit by looking at some results on a mathematical topic. I chose to look at arithmetic progressions because there have been some results in the news recently about these. So first, we'll look at a family of results around papers around Semerati's theorem. Then we'll look at a second family of results around Roth's theorem. So first, let's start typing a search where I want to have the search terms anywhere. And notice that as I start typing any, MathSciNet is offering me the ability to choose the field code for the anywhere search. Now I can put in the term here, arithmetic progression. Then come over here and execute that search. I get 7,421 results. Now, if I didn't know that there was a field for anywhere, I could click Show All Fields, and I get a list of both standard and advanced field codes. Come over here, click Any, and it puts that field code and the correct syntax into the search box for me. And again, I can type in arithmetic progression. And then this time I'll click Enter on my keyboard. And again, I get 7,421 search results. Now I want to take advantage of some of these filters that we've built in. Well, first of all, I want to look at some research results. So let's refine to journal article. So I come down to the facet on the left-hand side of the page and click journal article. MathSciNet tells me that these changes are unapplied. That's because before any search or any filter is going to be applied, I have to tell MathSciNet to apply it. Why do we do that? Well, maybe I want to look for journal articles and theses. Well, now I can click both of those field terms and then hit apply. Still have 6,700 plus results, so let's resort these by citations. Well, I was hoping to find Semerati's theorem, and now at the top of my search results, I see a paper by Semerati with 448 citations. Let's take a look. It says on sets of integers containing no k elements in arithmetic progression. And the review tells us that by an ingenious and complicated elementary method, Semerati has settled a conjecture. That is that pick an epsilon greater than 0, an integer k, then there exists a number n of k and epsilon such that if n, little n is bigger than big N, and R is any set of non-negative integers, all of which are smaller than little n, and the size of the set R is greater than epsilon n, then R must contain an arithmetic progression with k terms. Think of epsilon as a sort of density, so that if you have more than a certain density of integers in this set between 0 and little n, then you're necessarily going to have some of them in an arithmetic progression. It also tells us that there were some special cases solved earlier, k equals 3 and k equals 4. And if I click on these, I can get right over to Roth's paper. That was the special case. Let's go back to our search results. We come down and we see that the third item in this list is by Gowers, Tim Gowers, and it's a new proof of Semerati's theorem. The fourth is by Harry Furstenberg, and it also has Theorem of Similarity in the title. Indeed, all three of these papers are proving the same theorem, but using very different methods. Let's look at Furstenberg's paper, and we can see that he's using proofs using ergodic theory. We look at Gower's paper. There's a very long review of this, and we can see that he's using more advanced results, which are actually developed by him and led to his work that got him the Fields Medal. Our reviewer in the end, who was Furstenberg, points out in the end that the paper is a model of lucidity with each new idea clearly motivated. The author's effort at clarity make this a profound yet readable paper. Coming down here, the sixth paper on this list is by Ben Green and Terry Tao. The primes contain arbitrary long arithmetic progressions. This was a pretty famous result when it came out. And here it's taking a sort of variation on the similarity theorem to show that so long as you're looking at all primes, you can find arbitrarily long arithmetic progressions in them. This was quite an amazing result and was one of the several ingredients that led to Terry Tao winning a Fields Medal. Right, let's go back to our original search window. And I said that there was a second thing, which was Roth's theorem. So Roth's theorem addresses a different aspect of arithmetic progressions, and it relates to a conjecture of Erdős and Turan that basically asks how many numbers smaller than some ceiling, say capital N, can be put into a set without creating any three-term arithmetic progressions. So let's see if we can find Roth's paper. So first, let's put in Roth's name as the author of the paper. Now, as I'm typing that, it's trying to offer some suggestions for Roth. And let's just say that I don't know what Roth's first name really is. And let's say that I want to find the word progression in the review for the paper. So I click on R for review, search within the review, and put in the word progression. My browser is set up to autocomplete P inside parentheses into a special symbol, so I have to put a little space in there. That's my fault, not MathSciNet's. So I search for Roth as the author and progression as a word in the review, and I have 7 results. Now, I could go through these one at a time, but I did that ahead of time. And the key result here is this paper on certain set of integers. Another way that we could have discovered that, or at least made that our first guess, is look to see which of these papers is cited the most. Most of them are 3 to 10, maybe 20 citations. Then we get down here to on certain set of integers, and it's 252 citations. Very short review by Paul Erdős himself. He says, it tells you what the Roth result is. Denote by A of x the maximum number of integers not exceeding x, no three of which form an arithmetic progression. Then the author proves that A of x is less than C of x divided by log x. In a previous paper, the author proved that A of x was a little o of x. Now we can go from this and see, what other papers are related to this. So we can look at citations. These are other items in the MathSciNet database that cite this paper either from its reference list or from the review for the paper. So here we have 249 papers that are citing this. And again, we can do some filtering on this. We can look for the papers that have the greatest number of citations. Again, we see the papers by Gowers and Green and Tao. And we can filter these again. Coming down further, we can filter by the primary classification. I mean, maybe instead of looking at these things as number theory, we'd like to look at them as combinatorics. And here's a curiosity. There are people in computer science who are publishing papers that cite this. So maybe we'll just look at the computer science papers. And not a big surprise, but it appears that there are some connections between the Roth paper and Ramsey theory. Now, another way to have approached finding some of these results would have been to put some terms into the search field that are related just to our topic, not relying on the author's name, Roth. So let's try again with arithmetic progression and move outside of that. And we knew before that arithmetic progression produced a whole bunch of results. And so let's add inside the review the search terms 3 term, because that was the key to what was the content of Roth's theorem. We get 267 results. And again, an interesting thing is to filter by journal article and book collection article, say, and to sort by oldest or by number of citations. Now, another thing that we can do here is that if we're finding too many papers, and we can see that some of these are from 1940s, 1950s, we really want to see what the relevant papers are that are fairly recent. We can come up here, add yet another field code, which is the publication year. And I could just put in one publication year, or I can actually put in a range by just leaving a space between the 2 years. This narrows things down dramatically. And I see that now I have 206 matches. And I can start poking around in these and see what catches my attention. Let's clear this. And instead of using the new single box search with field codes, let's take a peek at the classic interface. So over here on the right, I click Show Classic Interface. And a set of boxes show up. And I can click on these and I can see the same fields that were available in classic MathSciNet. And so I can start searching just like I did in old MathSciNet. So I can put in the word Samaretti for the author. In the title field, I can put in the word progression. And here I can put in a year range if I want to, but I don't remember what year Samaretti's paper was published. Click that search, and now I have 11 search results, all papers by Samaretti, and all having the word progression in the title. Now, to sort of help you move from the classic interface to the modern interface, we collapse the classic interface in the list of search results, mostly because it takes up too much space. But you can see up here how that classic interface translated into a search in the new form. One other thing that I'd like to show you is a way that you can export the results from any search result. So let's do that while we're here. So to do that, I click on this link that says export, and all of a sudden the appearance changes. First of all, every match now has a little box by it, and those are check boxes. If I click the box up at the top, it'll check everything down below. Clicking again unclicks everything below. So now I can pick some of these items and say that these are the ones that I want to export. Well, the export defaults to BibTeX because we know from our logs that BibTeX is the most popular output that people want. But you could also use EndNote or AMSRef. Now I click Get Citations, and a box appears that has all of the clicked items displayed in proper BibTeX format. And of course, all of these BibTeX items, the bibliographic information is checked by our catalogers. And so there's every reason to believe that these are right on the money. How do I get them into my BibTeX file? Well, I could click inside this and highlight everything, or our programmers have set up this nice feature. You just click copy, and it tells you that it's now copied to the clipboard. Then over in another window, I open up my BibTeX file and copy it in using whatever my preferred editor is. Let's clear this again, move on to an author search. As I said at the beginning, an author search is going to lead you to an author profile page. So let's work on that. So as I start typing an author's name, MathSciNet starts auto-completing, or more properly, auto-suggesting. Well, there are a handful of mathematicians named Serre. Jean-Pierre Serre is a well-known number theorist, algebraic geometer, topologist. Denis Serre is a well-known analyst. Let's see what MathSciNet has to tell us about Denis Serre. Now notice that when I clicked on Denis Serre, what happened was it put his name up in that box. This is again a feature where if we did it instantly, then you'd always be stuck with what we gave you. Instead, it puts the name up there and you can change it if you want. You could reduce it down to just D Serre or keep it as Denis Serre. Now I click on the search button and I find a unique match. Well, that was kind of what I expected from the autocomplete. If it's saying there's somebody in the database named Denis Serre, I expect to find just one person. The author profile contains much of the information that's familiar from the old author profile. You know, the author ID, date of the earliest index publication, the total publications, total related publications. These are publications where Denis Serre is related to it, but is not actually the author. Very common thing is that he would be an editor of one of the papers or editor of the book that contains papers, or maybe there was a birthday celebration for him, and so there is a volume dedicated to Serre. Then if Serre has been writing reviews for MathSciNet, and you see that he's written over 200, it lists the number of those, and of course, all of these are clickable. We also list the total citations that Denis Serre has. He has 3,330 citations in 2,434 publications. That means that some of those publications cite more than one of his works. We still have the link to Serre's entry in the Math Genealogy project, and clicking this link will open up the collaboration distance feature with Denis Serre already filled in. Then you put in somebody else's name. See what the collaboration distance is going to be. Continuing down on the main author page, we list now as a table all of the classifications in which Denis Serre is published, and we've cataloged them in MathSciNet. If I click on the name of the classification or the number, it will take me to the page that explains what that classification is. If I click on the number of publications, it will take me to those 125 publications in MathSciNet that are in classification 35, partial differential equations. And same with any of these. By default, we show just a handful. Denis Serre is written in quite a variety of subjects. We can show more of them by clicking the Show More button. Over here, we have a table instead of a word cloud of the co-authors of the primary author on the page. And again, these are all clickable. If I click on the name of a co-author, it takes me over to that co-author's author page. If I click on the number, that takes me to the papers that the co-author has written in conjunction with the author on the main page. Serre has 42 co-authors. We're showing 5 of them. We can expand that a little bit more, We can go whole hog and show all of them in one batch. And then I can go back to just showing 5 of them. What's new in next generation MathSciNet is we now list the author's publications inside the profile page. And you can sort them by which ones were most cited, or just by the way they come up normally. Or I can click on this filter button, which looks like a funnel and has the word filters, and bring up the filters that I saw before in a standard publication search. I'm going to leave those alone. If I click on reviews, I can see the 235 reviews that Denis Serre wrote for us. And related, I can see the 9 items we have in the database that are related to Denis Serre in that he's not necessarily the author, And these all look to be things on which he is an editor. Going down the page further, we show the journals in which the author has published most frequently. So for Denis Serre, the most frequent journal is Compte Rendu, and he has 13 publications in there. Clicking on the name of the journal will take me to the profile page for the journal. Clicking on the number of publications will show me those publications. We also have a box that lists all of the series in which the author has published most frequently. And so here he has 5 publications in Pittman Research Notes. And if I want to see these in alphabetical order, I can just resort them by alphabetical, or I can do it in increasing order of number of publications in the series. Same works for the journals. So that shows you an author profile page. Let me show you a journal profile page. So we were looking before at some things related to arithmetic progressions. A journal that occurred several times in those lists was discrete analysis. So as I'm typing the title of the journal, MathSciNet is offering some suggested completions. So let's click on discrete analysis. Again, it doesn't execute the search, it just completes the title in the search box. I click discrete analysis, and I find that there are several things that have the term discrete and analysis in the title, and this is the one I want. The journal profile page is very similar to what was in classic MathSciNet before this new iteration. We have a box with the journal details, which is mostly bibliographic information. There's a link to the publications from that journal that are in MathSciNet. The earliest issue that we have in MathSciNet and the latest issue. We give some data about the journal that we compute. The mathematical citation quotient is a normalized count of the citations in the journal. We look to see how many citations it's received divided by the number of papers. And that's described in our little mouse over description tab. And here, there's a graph of the math citation quotient, which we just call MCQ. And since this journal started in 2016, we only have data for it for the more recent years. The orange gives you a benchmark. That looks at all the journals that we have in the database and computes the median MCQ for each year of those journals. So you can see how this journal compares with the others. As you can see, it's well above the median. If you want to take a picture of this for any reason, this little camera icon gives you the opportunity to save that image as a PNG file. Alternatively, if you want to pipe this into a spreadsheet or a CSV file or whatever your favorite computational file is, you come over to the table and it gives all the data for that journal for computing the MCQ, but it has the year, the computed MCQ, and then the ingredients that would tell you how to do that. For 2021, over a 5-year period, it had 105 citations, and over a 5-year period, there were 100 articles published in that journal. 105 divided by 100 gives you exactly 1.05. We also show you just a graph of the citations. Now, since this is a newish journal, there are no citations from 1990 to 2015, but we have this nice slider bar, so you can just focus on the years that are most interest. Again, we can convert this to a table. We can also look to see what journals are citing discrete analysis most. Well, it turns out that it's citing itself the most: an Electronic Journal of Combinatorics, Israel Journal of Mathematics, Ergodic Theory, and so on. And you can also get these journals in a table. We list the number of publications in the journal per year in this graph. And again, you can convert that to a table. And again, clicking on the camera icon will give you the chart as a PNG image file. The last two blocks of information give you information about the classifications, that is, the MSc two-digit codes that are occurring most frequently in that journal. For discrete analysis, not surprisingly, the top two subjects are number theory, that's MSc 11, and combinatorics, that's MSc 05. And again, clicking on the 05 would take me to the description of that classification. And clicking on the number of papers in discrete analysis in classification 05, I will see what those papers are. The default is to show you the numbers, the counts for the last 3 years. You can also see it over all time. Discrete analysis is a relatively new journal. Don't expect that the ratios of these things, proportions of these, are going to change much. If you looked at an older journal, such as Proceedings of the American Math Society, the change between the last 3 years and all time can be quite dramatic. Finally, we have the card of top authors. And again, we default to the last 3 years, and we can see who's published the most in this. And if I click on the author's name, it takes me to the author's profile page. And if I click on the number 2, it'll show me the 2 papers that Bill Jackson has in that journal within the last 3 years. If I look over all time, the names change somewhat. Terence Tao is now the most published author in the journal, and another list of people that are in the 3s and 2 range. And we can go down. Show all does not really mean show all for journals that have a huge number of authors. I believe we cap it at 100 or 200 authors. I'd mentioned that one of the things that's great about the new MathSciNet is that it works well on small devices, on phones and iPads. I can't really show that to you because I'm not using a phone and I'm not using an iPad. But what I can do is tell you that from the very first empty screen on a developer's page, we were thinking about phones and tablets and laptops and desktops, single screens, double screens, small screens. And so all of the layouts and the features and all the functionality were designed so that the important features work well in smaller formats as well as in large formats. Sometimes this means that a menu is going to collapse to an icon, such as the 3 stacked lines known to web designers as the hamburger, or descriptive labels are going to be abbreviated. For the filters on a small screen, the sidebar is going to be hidden by default, and it'll be displayed as a button above the first result instead. Then when you tap on filters on your phone or your tablet, it will be presented as a scrollable overlay. course, as the device and their screens become bigger, more of the options are automatically displayed rather than requiring a tap on the screen to expand them. We've also made a very big push right from the beginning to make this usable and accessible to as broad spectrum of people as possible. This has been a great development for MathSciNet in general. All of the choices of colors and contrast levels, fonts, and font sizes were made for increased clarity. And this helps all of the users, but it also is beneficial to users with visual impairments. We've also made sure that all navigation is possible by either a mouse or a keyboard using tab and arrow keys. And we've made sure that pages have embedded headings so that they're compatible with screen readers. The new version of the filters, which I showed, when you select one of the filter items, it doesn't activate right away. This helps people who are working with a screen reader or just with a keyboard. But this two-step process also opened the door to allowing multiple selections. Or it allows you to take one of these items and click it twice, turning a please include that to a please exclude that term. So it's been a great experience for us to be adding all of these new features to make MathSciNet accessible to everyone who's doing mathematics. And so this is something that I and the whole development team are incredibly proud of. Finally, all of the functionality is built on top of the careful, informed process used by mathematical reviews for the last 80+ years. MathSciNet is created and maintained by mathematicians for mathematicians. 80 years ago, it was created by the American Mathematical Society to serve the needs of research mathematicians. We continue to have 17 full-time PhD mathematicians working at math reviews. Their training goes into the selection, the curation of material, matching reviewers to publications, and editing the reviews. We also pride ourselves on the bibliographic accuracy of the database. We have librarians and trained catalogers on staff to ensure that accuracy. We are particularly proud of our ability to identify authors, especially our ability to distinguish authors with similar or even identical names. Every review in MathSciNet is read by one or more of our highly trained copy editors. Not only do they tidy up the language, grammar, and spelling, but they also make sure that citations within the review are correct and correctly formatted for linking within MathSciNet. So I and everybody at Math Reviews and everybody at the AMS hope that you learn to use all of the new functionality that we're giving you in this next generation of MathSciNet. There's a lot of information in the Math Reviews database, and we hope that you can make full use of all of it. And I hope that you enjoy the new interface as much as I do, and look forward to having questions later on. Thank you.